Hi everyone. Today we're going to be looking at the second part of waves. It has to do with reflection, refraction, and is only for the triple physics group that are doing this topic. As you can see that for the targets 1 to 4 there is nothing, so that it does not apply to lower level, but if you're aiming for 5 and above, you have to know specific things regarding this. So one of the key things that pops up is that waves can be reflected at a boundary between two different materials. To begin with, I will also explain what we mean by a wavefront, because that's something that you will see in your course. So one good way of looking at it is this diagram here. So what we have, the red lines actually represent, so you can see these red lines here, they actually represent, consider them as the ripples on the surface of water. So you placed a long ruler, for example, here, and you have a tray of water, and you start moving this ruler up and down. And once you do that, you're going to create waves, and this is what you see as this red colored line here. Obviously, you have loads of them because it's not just one wave that you're creating, it's actually causing every single particle to oscillate, and they're all oscillating in sync if there is no other oscillation in the process. Wavefronts are simply a line that joins the peak of every single wave along the line. So you can see that these lines show the peak of a wavefront. So it's easier for us to draw, for example, water waves using wavefronts. And we also know from our definition that since I'm picking the distance between this point to this point, is actually the distance between two adjacent points on a wave. So you have one wavelength. So the distance between two wavefronts is equal to one wavelength. There is nothing more special to wavefronts than just simply that. We use it to join the points that are oscillating together in phase, so they're reaching the peak together, and therefore it's a straight line. If I create straight waves from using a straight ruler and dipping it in and out at a specific frequency. So why do we care about that? Because we will be using this in diagrams. So what we are showing is the front of each wave as it travels. So this is the front of each wave as it travels across the water surface. What do we also mean by a boundary? It could simply be anything that blocks the waves from traveling in the same direction. It could be just, the end of the tray, or it could be the side of a lake or whatever, a mirror that we placed in the path of it. And this happens with every single wave. It's not just water waves. I wanted to mention it here. It's not just water waves, and I will also show you a couple of ways that we do represent waves. So this is the first one, when we said wavefronts. We also tend to represent waves in terms of in a straight line that shows the direction of energy transfer as well. So we show them as rays. Obviously, we can do that with electromagnetic waves because it's simpler to show them as the direction in which the energy is transferred, which is always in straight lines. But with water waves, we tend to use wavefronts mostly. And I will show you this to you in a second. So let's have a look at what happens in reflection. We have an incident wave. So we call it incident because it's the one incoming into the barrier. So this is our barrier. Let's say we placed a little ruler in a water tank. And what we have is the red lines are showing the incident wave. So these are the wavefronts. Remember, if I place just one wave here, it will be like this. So I have a wave coming in, that joins up all the peaks. So remember, the distance between each wavefront is one wavelength, and you can see that because it's the distance from two adjacent points. I'm just going to remove it so it's easier to see what's going on without the wave now. Now what we have is we have an incident wave. We're showing you here the wavefronts of it coming in, so incident wave. And you can see the blue lines of the reflected wave. And you can also see these arrows that are straight. Now if you notice that, they are 90 degrees. The wavefronts and the ray wave are 90 degrees to each other. That's very important because it will make it very easy for you to draw when it comes to exam questions. So we have this wave line coming in. When it comes to light, light travels in a straight line. So we will usually represent it as a light ray. So I'll have this incoming light ray. When it comes to water, we have the wavefronts usually. And it touches the barrier at this point exactly here. Now whenever any wave is incoming, whether it's a wavefront or a wave ray, light ray, always remember that it's useful to have these straight lines as well. And at 90 degrees to the actual surface that is touching, we always draw a normal line. The normal line is to show us clearly the incident angle and the reflected angle. So what we have here, this part, this angle here, we call it the incident angle. So that's the angle it makes between the ray and the actual normal line. We call this line the normal line. Then what you see is the reflected wave. You see that's wavefronts and as a ray. And this angle is actually 45. Yeah, that's 45 degrees. And if I go to this one, this is also 45 degrees. And we see that the ray is also reflected from that. Oh, oops, no, my bad. So we see that the ray is reflected at exactly 45 degrees from that point. So you know now that when something reflects off a surface, it is actually the angle of incidence, should be equal to the angle of reflection. So we call this the angle of reflection. So what you can see from here is that when you what you have in reflections, you have a wave that changes direction. So we have this wave coming in, and it changes direction at this boundary. So we call this barrier the boundary between two different media. So this is one medium, this is the second medium. So this is water, this is just a ruler or some plastic piece that is blocking the wave from traveling past it. But it still remains in the original medium. So this is what reflection is. So we saw wavefronts, wave rays, because it could come up in your exams as a light or water wave or even sound waves. So you need to be aware of how to use both of them. So the easiest way I will tell you to do this is to always draw the straight lines first. Even if you're given wavefronts, always draw a straight line, find the angle of incidence, then draw another straight line that's exactly equal to the angle of reflection, and then proceed on to draw the wavefronts at 90 degrees to it. This is the simplest way that you can do it. This is also a very good point to mention that the wavelength, frequency, and speed remain unchanged throughout the reflection. So there's no changes in any features of the wave. So we said waves can get reflected at the boundary. This goes for every single type of wave, not just water waves, not just light waves. Sound waves can get reflected, but they can also get absorbed or transmitted at the boundary between two different materials. And that depends on what type of wave that we're dealing with, what type of material. So for example, we have a glass. So this is the cross section of just a good normal glass. What you have is the incident wave coming in. So let's draw it with amplitude so that we can see that. So we have a light ray coming in. As it passes through the glass, some of it could get absorbed, so it will decrease some of the energy of the light could get absorbed, so it could decrease the actual amplitude of it, and some of it will get, for example, transmitted outside of it. Some of it will also get reflected. So this is in a general diagram. So this is the absorption, so it can be absorbed by material. For example, the people that use tinted windows in their cars, the reason that you cannot see through them is because most of the light gets absorbed by that glass. The reason that you can see through other normal car windows is because the light gets transmitted through the material, and reflections usually is what causes a bit of a blur in your eyes when you look at it, and you can even see your own reflection sometimes on the windows of the cars. Another good example is microwaves. So microwaves usually get absorbed by the food because they're used to heat it up. They used to heat up the water molecules actually in the food. And so they get absorbed by that, but they get reflected by metals. That's what causes the extreme heat if you put metallic materials inside a microwave. But they do get transmitted through the glass window, and usually what they tend to do is place a specific material inside the door so it absorbs it as well, so it doesn't come out of the microwave. As you can also see from the specification, there's required practical activity that you should be able to describe. And it says that to investigate the reflection of light by different types of surfaces. I will put a link in the description below of a nice YouTube video showing how to do this. The main key things to always be careful of is the normal line, showing how you're going to measure the angle, always including your equipment. So you should be able to describe how to perform this experiment, and also make sure that you always include the equipment. You'll find the link in the description below. The next bit that we should be looking at, it says students should be able to construct ray diagrams to illustrate the reflection of a wave at the surface. We've seen this. We also seen this not with just rays, we've seen it with wavefronts, so that's perfect. And then it says you should be able to describe effects of reflection, transmission, and absorption of waves at material interfaces. We spoke about the reflection. We mentioned transmission, but I'll go deeper into that. And absorption, as I said, if a wave gets absorbed, a lot of the energy of the wave gets absorbed. So usually that will affect the amplitude of the wave and hence its energy that is carrying through. So we'll have less energy when it gets transmitted. So let's go on through transmission. We're going to have a new word here. This is what we call refraction. So here we talked about reflection. We talk about the relationship between angle of incidence and angle of reflection, but this is for refraction. And we will talk about, and we spoke about how partial absorption results in amplitude, because some of the energy of the wave is absorbed by the actual material particles or molecules or atoms. And we will describe refraction now. So let's start with what refraction is. Now, refraction is a change of direction of waves when they cross a boundary between one medium and another medium. We'll talk about firstly the water waves, and then I will talk about light, because that will be another thing that you need to be able to perform an experiment, or at least describe the experiment that is involved with it. So what we do for water, because obviously if you have water waves in water, the only thing that you can change is the depth of the water. So let's assume this is the side view of the ripple tank, and I created the waves, and then I placed a little block there that is used to basically change the depth of the water. So what you see here is you see this depth, and this one has a less depth than it. So you can see that this is to make the water shallower along this end. So this is the deep end, this is the shallower end. When you look at the top view, so if I look at it from the top, and remember once again, these are the wavefronts that are joining each peak of each wave. So I'm looking at the peaks of all the waves at each point. This is where I place my block at an angle. You can't see it from here that the block is at an angle, but from the top view, it is at an angle. And that's important, and I'll explain that very, very soon. So first things to take into account when it comes to refraction, we consider that this is the boundary where the medium changes in terms of water waves. So we have the deep end and the shallow end. And since this is at an angle, I will always, again, reflection and refraction both need for you to draw a 90-degree angle to the surface. So a line, we always draw the normal line as dashed line because it's not really taking any part in it. It's for us to be able to measure the angles. And I know this might not seem useful now, but those angles are used later on in A-level physics when we look at calculations involving them. For your GCSE course, you don't need to know about it, but it's very useful at least to get used to the terminology, especially if you're trying to continue on with physics, which is the best thing to do. So you have the normal line. It's always at 90 degrees to the boundary between the two surfaces. So this is exactly where the depth changes. So that's why we call it the boundary. So what you have in refraction is that you have the waves coming in here, and then at the boundary, so when there is a change from one medium to another, the direction of the waves changes across the boundary. So you can see the waves where the wavefronts were facing this direction, and now they're all of a sudden facing a different angle. And we will explain how this works. So as these waves start entering the shallower region, what happens is that they slow down. So water waves travel slower in shallow water. So what you're experiencing here, you have the equation of measuring the speed of waves. So you have speed of wave is equal to the frequency times the wavelength. Now the speed decreases as it enters. So what you see at the beginning here, at this section, is you have this part of the wavefront entering and changing speed. So as each point on this wave is traveling slower compared to this part of the wave, you experience that bend. And if you notice, the angle of incidence is actually a bit bigger than the angle of reflection. So every single time a wave slows down as it enters a second medium, the angle of refraction gets less. So this is angle of refraction, sorry, not reflection. This is refraction part. So what you have is each part of the wave slows down, and hence since it slows down, the speed decreases. And now you also need to know what happens to frequency and wavelength. Frequency does not change because you still, even though the waves slow down, you're still creating waves, let's say by dipping a ruler in a water tank. So you still have the same frequency. So the rate that the waves are being passed from one medium to the other is still the same. The only thing that can change is the wavelength, and you can see it because the difference between these wavefronts, which is one wavelength, is bigger than the difference between these two wavefronts, which is lower. And you can see it from the side view as well. The wavelength is bigger than when the waves are passing through the shallower region. So they get closer together, the wavelength decreases, the speed decreases, but the frequency remains the same. That's actually popped up a lot in exam questions, and people tend to lose a mark or two here. But there's also another exam question that I will go through now. So a very common exam question states, for example, explain why refraction happens at the boundary between the deep water and the shallow water. Is what we already said. So you have the velocity is slower in the shallow water. So the edge of the wavefront entering the shallow water, so this part slows down as it enters, but the other part of the wavefront is still continuing at a higher speed, leading to a change in direction of the wavefronts. That's all you need to know in order to explain what is going on at refraction. But what if I didn't have this barrier that are placed within the water, so this block that are placed at an angle? If I didn't have it at an angle and I had it at 90 degrees to the wavefront, so I have my wavefronts coming in, have my waves coming in straight through a barrier, so you can see the depth of this side is more than the depth here. And you also see that I placed the barrier in a straight line, not at an angle like here. It's been placed straight in a straight line. So it is aligned straight away with the wavefronts. So why am I not experiencing a change in the direction? Because here we see the wavefronts changing direction, but here we don't. But we only see the actual speed changing because the wavelength here is bigger compared to the wavelength here. The frequency, once again, remains the same. Frequency always remains the same. It's only the wavelength that changes, and hence the speed. So if wavelength decreases, speed has to decrease as well. And we see here that obviously this is the shallow end since the wavelength decreased. So why is it not bending? Well, in this case, every single point, so this is another common exam question. So every single point on the wave enters and hits the shallow water at the same time. So every point slows down exactly at the same time. Otherwise, it would have been at an angle. Going back to what you should know for your course, to explain, we discussed how to explain refraction and reflection using the wavefront model. We described the relationship between the angle of incidence and angle of refraction. So remember here, if a wave slows down, the angle of incidence is bigger than the angle of refraction. And if it speeds up, the angle of incidence is less than the angle of refraction. Explain in terms of refraction in terms of changing speed, that's done as well. And describe refraction, we've done it as well. The last speed we need to look at is the refraction of light by different substances. I don't have the equipment at home to record the experiment, but I will put the second link in the description below about how to do it. I will discuss, however, quickly how you could do it using a few pictures. So here we have a glass block. You will also need a source of light. You won't be given lasers because it's simple to use a light bulb and a barrier to just allow one ray, or a concentrated light ray to go through. So you can see these bits trying to go, but you can't see them clearly. It's a bit more of a focused ray that you need. And you will always need to draw the normal lines to the surface, whatever you do. So the first thing that you will do is draw around your block. So just get a pencil, draw around it, and then draw the normal lines where you're trying to aim the ray at. You will need to use a protractor to measure. So you need to draw this once you turn on the light. you need to draw a line for that using a ruler, you know, to the best of your ability. Another ruler to draw the one outside. Obviously, if you have the block there, you won't be able to draw the one inside, but it will be very easy to do so after. It's a good point to mark here 90 degrees to the surface as well, because that's another normal line where the light rays entering, exiting. So remember, refraction doesn't only happen for water waves, it happens for every type of wave nearly, actually for every wave, yeah. And light waves are usually the easiest ones to measure and complete an experiment through. So what you will then do is remove the glass block and join these two lines together. That will give you the opportunity to measure the angle of incidence, which, remember, once again, is this imaginary normal line, is the angle between the imaginary normal line and the actual ray. And then your angle of, so this is angle of incidence. And this is your angle of refraction. And you notice that this line is actually parallel to the one that's coming out, because as light enters the block, so it's faster in air, so light is always faster in air. As it enters the glass block, it slows down, moves towards the normal, because the angle of refraction is smaller. And as it exits back, it speeds up, the angle of refraction in this case increases. So it depends on which direction it is going to. So this topic involves quite a bit of experimental work. Don't get panicked through it. The first thing that I will go through as part of the specification is how to measure the speed of ripples on water surface. You should be simply able to state, for example, how to measure the wavelength and frequency of water waves in order to get the speed. That's what you're measuring, right? If you want to measure the speed of any waves, you either need distance and time, or you need frequency and wavelength. So how can you get those values? We'll start with what a ripple tank is first. So what we have here is a ripple tank. It's simply a shallow tray of water, and so this is a tray of water. What you have is a motor used to move this oscillating paddle up and down, so it can create the wavefronts that you see as darker lines. And then you have the light, so you can project the waves at the bottom. Now there's a device called a stroboscope, so it's a flashing light. And if you match the frequency of the stroboscope with the frequency of the wave, so there will be a dial that you can twist and turn like a gas a stove or something, where you can alter the heat of the fire with the dial. So the same thing that you can do with a stroboscope, you can match the stroboscope's frequency with the frequency of the waves, and it will make them appear frozen. So then you can use it to measure the wavelength, so the distance between the two dark spots, or the centers of the two dark spots that you see on the mark there. So for example, you can even take a picture with a ruler placed there, and then measure the distance between these two. Now, to make it more accurate, so when you are asked in exam questions or describe an experiment and include how you can improve your accuracy, then you can actually say that you measure the distance across the number of waves. So for example, between 5 waves, so you can, or 10 waves, so you can measure through from here, from this wave to this wave, for example. And then the distance that you get, you will divide it by the number of waves between them. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, for example. So whatever distance you get here, if that's 9 centimeters, for example, and you have 9 waves, and you divide 9 centimeters by 9 waves. So each wave has a wavelength of 1 centimeter. as an example of making an improvement, not just measuring one wavelength. So you could take a picture of it with a ruler there already. Don't forget to always mention the equipment that you're using, otherwise you won't be getting the marks for it. You can't just say, I'm going to measure the wavelength. How are you going to measure it? There's the whole point of you describing a method. It's common mistakes that people forget. So you could then use, for example, the stroboscope measurement that you took. So you use the stroboscope to freeze the wave, to make the wave look like it's frozen. Then you can take straight away the reading on the dial of the stroboscope, which will give you the frequency. So you already measured this method, the wavelength. And you need the stroboscope to give you the frequency for it. I will put another link to show you in the description for you to see how that experiment can be done as well in a number of different ways. So you always mention how you will measure the wavelength, what equipment you will need, how you will measure the frequency, and hence how you can collect the speed of the water wave. So that's the whole point, that you want to measure the speed of ripples on water surface. So you multiply the two numbers and you get the speed, but that's not enough. You always need to make sure that you are repeating your measurements. So you could change the frequency using the power supply. There's always a dial usually that allows you to change the frequency. You repeat the steps and you get the speed. Now, obviously, since the depth of the water is the same, the speed should always be the same, but it gives you a graph that you can draw and hence get the a better average of those values for the speed. Another way that you could get the frequency, if you don't want to remember the stroboscope, is to actually record it in slow motion. So record it and then play it back in slow motion. A very useful thing to do is place a marker, for example, let's say there, and record it for a minute, then play it back and see how many wave fronts have passed this point in that 1 minute. So, but you have to play it back in slow motion because it's going to be too quick for the human mind to measure. And usually depending on the frequencies that we're using. And once you play it back in slow motion, you can count the waves, divide the number of waves you counted in 60 seconds by 60 to get, the frequency per second. And that way you can find the frequency. So it's not only the stroboscope as an answer. You can always record it and play it back in slow motion. Very, very important. So it says describe for targets 1 to 4, because this is something that everyone is required to know. So describe how to measure water wave speed using the ripple tank. We just described that. The other part that we will be looking at today is how to measure sound wave speeds, and I will explain that now. So there are several ways you can do it, but I'll go through a couple of them. So first method is you can have two people that are standing a fixed distance away from each other, and this distance needs to be known. You can measure it if it's for example, 100 meters or more, because it is necessary to be quite a long distance between them. Usually a good way of measuring that is using a trundle wheel. That's a good point to start. If you don't know what it is, just Google it very quickly and you'll see that. Then when you do measure it using the trundle wheel, one of the two people will have to have, for example, 2 wooden blocks or cymbals. So those loud metallic instruments that you can knock together. So the one person holds the wooden blocks or cymbals above their head. The other person, on the other hand, has to have a stopwatch. So as soon as this person hits the blocks together, this person should start the stopwatch, and then this person, still the same person, so they first see the person knocking them together, they start the stopwatch, and they stop it as soon as they hear the sound. The reason this can be done is because light travels much faster than sound. So when the person first sees the blocks being knocked together, the sound takes much longer to arrive to the person, which gives it an idea of how long sound took to travel towards them. So by knowing the distance and knowing how long it took for sound to travel to that person, we can use the equation speed is equal to distance over time to calculate the wave speed. As I said before in the first part as well, you can use this equation to measure wave speed as well as the other equation. Depends on what equipment you have, what experiment that you're doing, and which way is easier, because obviously you can't see the wavelength of sound particles, but you can see the wavelength of water waves. So that's the reason why it's easier to use frequency times wavelength for water waves, whereas not in terms of sound, because sound is not something that we do see. We don't see the real vibrations, we just hear them. And as always, before I forget, you always repeat the experiment at least 4 or 5 times. You take an average of the time it takes, and then you use the equation to calculate it. The second way of measuring the speed of sound in air is using echo. So an echo, just for those of you who forget, is the reflection of sound waves. So if you're standing in an empty school gym, or like in a very large empty hall that has bare walls, then if you make a sound, short time later you'll hear your echo. So that's your sound reflection. Again, in this case, you can have one person standing a fixed distance from a wall, so that's a wall. So that will be, I don't know, about, say, 50 meters. Use a treadle wheel to measure it again, or a tape meter. Then you have a person standing here. The person should make a really loud noise if they're using 2 blocks together and just hitting them together. And they should start a timer. So you should have another person that starts the timer as soon as they hit the blocks together, and then stop the timer as soon as they hear the echo coming back. What you have is, once the person knocks them together, you have the sound traveling this direction and then traveling back again as an echo. So that means that the time that we're considering is the total time it took for it to go there and come back. So that means that we have to use double the distance, since it covered double the distance. So we use again the speed is equal to distance over time. But in this case, it should be times 2 the distance, because we are recording it while it traveled there and back. So this is using, again, this person's using the stopwatch, this one's using the blocks, knocking them together, and it's all about timing, how long it takes to hear the echo return back. There's a third way of doing it, and in this case it involves using an oscilloscope and microphones. Now in this case we will use an oscilloscope and 2 microphones. I know they don't look like perfect microphones, but that's fine. Just use a bit of imagination. Now what you will have is set the 2 microphones, connect them to the oscilloscope. You have to arrange it so you can see the what an oscilloscope does. It shows you basically the wave created in the screen. So it shows you the amplitude of the sound. So if there is a vibration, a sound vibration, then it will be picked up. And it also shows it the amplitude against time, so as time goes along. So this is the amplitude axis, this is the time axis. So when you have them both microphones connected to an oscilloscope, you place them a fixed distance apart. So it could be 2 meters, 3 meters, 5, 10, so let's say 10 meters. You can measure this with a tape measurer, which is better. And so what you will do is trigger the first microphone to detect the sound. So you just can clap, make a loud clap. And what you will notice is that you will see a first peak, because that's when the sound arrived at the first microphone. And there will be, since you have them both connected, so you'll get trace for both of them, then you will see the second clap when it arrives to the next microphone. And the time between them, there's a time delay, obviously, that you can use. So you can determine the time at which the clap reaches each microphone and get the difference between the two claps. And you can repeat that a number of times to calculate an average, and then again use speed is equal to distance over time. You can see that with these ones, we don't need to double the distance all the time or anything else. It's only with the echo, because we know that the echo travels, so the sound travels one way, reflects and travels back. So we need to take into account the total distance traveled with the total time it took for it to travel that distance. In this case, there's no reflection, it's just continuously traveling to that one, so we don't need to change anything. So we discussed how to measure speed of waves in solid, the speed of sound in air. So that's one part here, describe how to investigate the sound of speed in air. Now, how can you do that in vacuum? Well, that goes back to this point here as well, where you have to state that sound waves need a medium to travel through. So if I placed a loudspeaker or even my phone into a vacuum container and then I pulled all the air out, I wouldn't be able to hear my phone ringing, because sound waves are longitudinal waves and they need a medium to travel through, so air. Otherwise, there's nothing that can transfer those vibrations. And you can do that using a bell jar and removing the air out using a vacuum pump. Once you do that, you'll notice there is no sound coming out of it at all. So if I put my phone there and it rings, I will not be able to hear it because I removed all the air particles. So that's another way of investigating sound in vacuum. There is no speed of sound in vacuum, is zero. There is no sound, obviously. Before I move on to any other experiments, I wanted to talk about this part here. So how to describe how sound wave speed varies in gases, liquids, and solids. Just a very quick reminder, gas particles are spaced further apart. Liquid particles are much closer together and they can move more freely. Then we have the rigid, fixed, solid particles that are stuck together, but they can vibrate in their positions. So when we have sound traveling in air, this particle, for example, as it's oscillating, takes a bit of time to reach this particle and collide with it, then cause it to vibrate, and so on and so forth. So the vibration has a time lag for it to pass through from one particle to the other in air. When it comes to liquids, though, the particles are touching each other. So if I push this particle here, it will push this one quick enough, and it will push that one much quickly, and it will go on and on. So the vibration will transfer very, very quickly in a liquid compared to a gas. Then obviously you have the solid, which they're already stuck together. So when this one vibrates, it will straight away cause a vibration in this one and this one and this one and so on. So speed of sound is actually the slowest in air, and it gets much faster. So longitudinal waves, like sound waves, get much faster in solids. So sound speed is higher in solids. So you should be able to describe how the speed of sound is lowest in the gas and it increases. So in normal air, it's about 340 meters per second. And if we look at a material, for example, diamond, for example, in diamond, they can reach up to 12,000 meters per second. So you can see the difference between sound traveling through air and diamond, for example. So moving on to the next bit, we did describe a method to measure the speed of sound waves in air. So these two have been achieved. Students, for physics only, students should be able to show how changes in velocity, frequency, wavelength in transmission of sound waves from one medium to another are interrelated. We did talk about this in terms of water waves and light, and I will go on to explain how that works with sound waves. So for this part, once again, if sound, for example, passes from air to water, and this is the boundary between them, the vibrations are at an angle. So we have the waves coming in this direction. This is your normal. And this is your angle of incidence. And since we know that the speed of sound waves increases, and remember these sound waves that we're talking about, if the speed increases, that means that the sound will move away from the normal. So the refracted angle will be bigger than the incident angle. And that's based on the fact that you have different densities and structures for air, liquids and gas and solids. So make sure that you know that difference. So that's the only part. Also, don't forget, even though the equation, we have it here, we said that frequency always remains the same. So if the speed increases, the wavelength increases. So if you had, for example, your incoming waves like this, then, and the distance between them is smaller, then the ones that get refracted in the water will be spaced much further apart to show that increase in wavelength. Frequency always remains the same. We also went through this part, calculate the speed of sound waves using their echoes. Some parts that we didn't go through explicitly, I did mention them, are these two. So describe how changing the wave frequency affects the wavelength. Now, this actually applies to us having a fixed speed and just simply altering the frequency. So in the case of a ripple tank, for the same depth of water, so in this case here, so for the same depth of water, I will only be able to have one speed. And if I change the frequency, since the speed is the same, that will mean, so if I have my V is equal to F lambda, if the speed is constant due to the same depth, then if I'm increasing the frequency, my wavelength has to decrease in order to accommodate for the same incremental increase or decrease that I tend to change it with. Now, if I decrease the frequency, the wavelength would increase to match the same speed. So this is basically already covered. The last thing that we're left to do, and I will also add, once again, a link in my description. It's another experiment that you should be able to describe, and it's a little bit harder than normal. You haven't seen that before, but it's a nice experiment when we get back to school to have a go at. So it is to describe how to measure the speed of waves in solids. Now, we're not talking about really big blocks of solids and stuff because we won't be able to measure that. We're talking about a single string and how we can use it to calculate the speed of waves formed on that speed, on the string. So this is a very simple setup. Obviously, you'll watch the other videos and you'll get a good hang of it. It's all about getting the right points here. So we have a signal generator. Signal generator allows us to connect a vibration generator and use a dial to adjust the frequency. So for us to change the frequency ourselves. The reason we need this is because we want to have, so this is a vibration a generator. So it vibrates, just simply attached to a string. And that string is attached to a hanging mass to keep the same tension in the string, basically, throughout the experiment. So we need tension in that string. So this is basically one end attached here, if you consider it, and the other end that's oscillating. Now what we're doing here is we're causing this string to vibrate. So this is the solid speed that we're going to be measuring. Obviously this whole setup should be based on a table, but I thought I'll simplify my drawing. And what we will do is adjust the frequency that this string is oscillating at in order to give us a standing wave. You don't need to know about what standing waves are, but you need to be able to create, to generate a standing wave. So just by adjusting the frequency slowly, you will be able to get a shape that looks like this. So it will look like it's going up. So this is where the vibration generator is, and this is the other end of the pulley there. So what you will end up seeing is this wire moving up and down so quickly that it seems to appear in two places at once. Like I said, watch the video in the link below, in the description below, and you will understand more. Now, there's two measurements that you can get here. Because we have a signal generator, we are adjusting the frequency. So we can use the speed is equal to frequency times wavelength. The frequency can be collected directly from the signal generator once we get this single loop only. And to get the wavelength, so we know already that one wavelength is like that. So half a wavelength is what we see formed on the string, on the solid. So that will be basically this length that you measure here. So you'll use a ruler or a meter ruler, depending on what you have, how long it will be. You can use that to measure the length. So if this is the length, we know that this length is equal to half a wavelength, because it's another half. This is a complete wavelength altogether. So that's equal to half a wavelength. So if you measure this length, you double it, and your wavelength is 2 times that length, times the frequency. That will give you the speed of the wave in a solid. We always need to repeat the experiments. So what you will have to do after that is increase the vibration generator's frequency using the signal generator. And you will end up getting another wave between those 2 points that looks like this. Another wave that looks like this. So this is the wavelength is actually equal to the length now. In this one we have 1.5 wavelengths, so that's 3/2 wavelengths. And so on. So you repeat it a couple of times. You always take the frequency from the signal generator here, and you multiply the frequency and the wavelength, and you get the speed, and you get an average for it.